It's happened. I've been given the ultimatum by my significant other that I either need to finish the kitchen backsplash or we need to hire a professional. I just can't let that happen. I mean, why would I hire somebody when for twice the price I can buy the tools and then I can drop hundreds of hours of my own time and do a mediocre job? Not hiring professionals and then getting in over my head is kind of my thing. The problem this time, though, is that this isn't a normal backsplash. A brief recap on this project. First, we decided to install these glass mirror tiles, and then I thought to myself, you know what would be cool? What if I added LEDs to each of these and then lit up the wall? I took that a step further and thought, what if each of these LEDs was individually controlled and an RGB LED? Then I could make a display out of the wall. And then because this project wasn't quite hard enough, I thought I should also add touch feedback so that I can make graphics that respond to taps. At this point I stopped thinking, and I started to turn this project into reality. To make this work, I'm creating around 200 circuit boards. Each one straddles 2 tiles. Each PCB has 2 microphones, 2 NeoPixel style LEDs, and a PY32 microcontroller that reads the microphones and returns the values to a separate, larger processor. The larger processor is the one that commands the LEDs and runs whatever display programs I can dream up. This is the 3rd video in this series. Go back and check out the other 2 if you haven't. I described the concept and the initial prototype in the 1st video, then I discussed programming the PY32 microcontroller in the 2nd one. Today, I'm going to try to make a bigger prototype, hopefully 12 tiles big, to prove to myself that this concept works at scale and that I can reliably make these circuit boards and mount them to the tiles. How hard can it be? I'm Zach, and you're watching Zach of All Trades. In the previous videos, I covered the concept behind the LED backsplash display, the general architecture, and how I plan to accomplish this feat. If you haven't watched those, I suggest you go check them out, and be sure to subscribe. I then made a circuit board to test this out, and well, it was really successful for a first attempt. The LEDs worked, I proved that I could light up the tiles, and I programmed the PY32 microcontroller to monitor the microphones for touch feedback. I even started to write code for the main controller. I was at the point where I was 90% done and 90% to go, at least in terms of development. In this video, I'm going to suffer through that last 90%. After making the last prototype, the first thing I did was create new circuit boards. There were a couple of problems I was trying to solve. First, gluing the boards to the tiles with this old geometry was kind of a nightmare. Because the back of these tiles are chamfered, getting the microphones where they belong means centering this board on the grout line. And that makes getting the LEDs into the right spot nearly impossible. I switched the geometry to this more elongated design. It's the same area, and therefore the same cost, but I'm hoping it'll be easier to mount. Another big issue with the previous design was that all the test points were on the back side of the board, the side that got sandwiched between the tile and the circuit board, and that meant I couldn't actually probe them once the circuit board had been mounted to the tiles. This made it easy to lay out, since the test points were on the back side of the board where there are hardly any components. But it was an obvious oversight, because I needed to probe those signals once the board had been installed. Another thing is that the programming pads were tiny, like 1mm diameter circles, and they were really hard to solder to, and they were prone to being ripped off. I switched to the same 4-pad footprint that I'm using for the ribbon cable, and that's making soldering much easier. Lastly, I added the option for a high-pass filter between the microphone's op-amp and the microcontroller. Here's my thought. When I touch the wall, a low-frequency, large-scale movement of the wall might be occurring. Since this could be large in amplitude, it might obstruct the rest of the signal and make it difficult to tell exactly which tile has been touched. By blocking out this low-frequency content, I can instead focus on the high-frequency stuff, which I believe will be more isolated and easier to distinguish. I will admit that I'm not really basing this theory on any hard data or anything I've measured. I just have a gut feeling that this might help. If anyone has an opinion on this high-pass filter, or signal processing in general, let me know in the comments. I'd love to hear some other perspectives. I made these design changes, sent the Gerbers out for fab, and a few weeks later, 9 circuit boards arrived at my door. I laser cut a stencil out of brass and used my solder paste stencil printer to apply paste to the boards. This didn't work perfectly on the first attempt though, so I made a few changes on this stencil, particularly on the microphones and the microcontroller. This is the second stencil. I just ripped the first one off the frame so I could reuse it. This stencil works much better. I'm certainly learning the tricks. I've made these 2 boards with this stencil so far, and they're working great. For testing, I've got 2 programming wires, the power and ground, as well as the LED signal in and a microphone value out. These 2 wires monitor the microphone output after the amplifier and the high-pass filter. I can hook these up to an oscilloscope to verify that they're functioning correctly. I've taped all these wires to the board to provide some reinforcement. These pads in particular are really tiny, and I already ripped one off of this board. I flashed the code to these, more or less unchanged from the first prototype, although I did find one bug, a classic case of using an OR where I wanted an AND. This seems to be working well, and the microphone signals look correct on the oscilloscope. I'm using a tone generator here to test this, and while it is quite annoying, the scope response is oddly satisfying. To do much more testing though, I need these appropriately mounted to tiles so that the microphones will have the correct response when they're tapped. But here's the issue. I've only purchased 1 sheet of these tiles so far. They come with 16 tiles each, and I cut 2 of them off for this first prototype. I found a bare one here, and I seem to have just lost one, which leaves me with 12 tiles. Now I'd like to make the prototype where it uses all 12 of these tiles, which would be 6 circuit boards. But to test these, I really need to epoxy the boards on, and then mount all these tiles to a wall. I don't want to just glue all the boards on and hope for the best though, because what if I need to make a hardware change or something? A related problem is that I only have 9 of these circuit boards, and one of them's already been populated and it only partially works, so I'm gonna have to be a little stingy with circuit boards as well. I think what I'm gonna do is this. I'm gonna build up a prototype with 2 tiles, so 1 circuit board, and I'm gonna mount it to a section of drywall with the signal wires and the programming wires sticking out the back. This will allow me to add more tile to the same prototype later and still solder the connections from the back. Then I can at least flash new code to the microcontrollers once they're mounted, if I need to, although I will not be able to make any hardware changes like swapping out resistors. If I need to do that, I'll build up another set of 2 tiles, 1 circuit board, and I will add that to the wall. So all the tiles might not be exactly the same, but this will allow me to test various changes side by side and still end up with a 12-tile prototype in the end. Another thing I've done is 3D print these little tile spacers. Unlike the crappy cross-shaped ones, these should locate all 3 adjacent tiles. I'm planning to just tape these down to the tiles to create a pretty rigid sheet of tiles before I glue the circuit boards on the back. That'll prevent these from flopping around and putting a lot of stress on the circuit boards. Okay, I'm gonna get this circuit board installed. Not so fast. I was up late last night trying to figure out this weird issue I was having. The microcontroller would seem to function fine for several minutes, but then it would just lock up. Oddly, this seemed to correlate with a really loud microphone input. Looking at the register values while in this error state didn't really make sense. It was like it had jumped to memory that didn't even exist. I checked the code that handles the microphone math, thinking that perhaps a large enough signal would overrun the memory and corrupt something, but this didn't seem possible the way I had it coded. I also spent quite a bit of time looking at the various interrupts and their priority levels and how often they occur, thinking that maybe the interrupts were stacking up and stopping some important piece of code from executing. But this also didn't seem to be the case, although it was a valuable exercise, as I did make several improvements to the interrupt priorities. I think I've finally figured it out. A quick recap on the microphone circuit. The microphones output a small analog voltage with some DC offset. This is fed through a DC blocking capacitor and into an op-amp. The capacitor removes the DC component, except I'm adding another DC offset by biasing the other input of the op-amp using this resistor divider. So the output of the op-amp should swing around VDD divided by 2. Remember that scope trace earlier of the microphone signal? Well, the scope is in DC coupled mode there, so that signal is actually swinging about 0 volts. And the reason is because I stupidly added that high-pass filter between the op-amp and the microcontroller. High-pass filters block low-frequency content, and they allow high-frequency content to pass through, as the name implies. And the lowest frequency content is DC, so that's being blocked entirely, and just the remaining high-frequency signal, which is swinging about 0 volts, is allowed to pass. A particularly large signal is swinging particularly far into the negative voltages, which the ADC is not equipped to handle. Its range is 0 volts to VDD. This seems to be causing a power glitch on the microcontroller, which is scrambling the register values and crashing the processor. I'm actually surprised that this hasn't damaged something inside the microcontroller. Regardless, the solution for now is just to remove the high-pass filter by putting a low-value resistor where the capacitor was and removing the original filter resistor. I may put a high-pass filter back into the final design, but I'll do that between the microphone and the op-amp, such that any offset applied by the op-amp remains. So it's a good thing that I didn't install this board yet, as I did end up having to make a hardware change. I'm hoping that from here on out it'll be just software improvements, so I'm going to get this installed. What I want to do here is take my 3D printed spacers, tape them in place where they belong, make the tiles nice and rigid, flip this over, and then glue the circuit board on. So I'm going to take this circuit board and I want to pre-bend the leads to about 90 degrees so that they slide into the space between the tiles. Okay, this is an epoxy I had laying around from a different project. It is a little milky, so I probably won't use it in the final build to glue the LEDs on, but for now, I think it'll be fine for the prototype. I'm going to apply a couple dots to the microphones and then around this side of the board and stick the whole thing down. I should also add that for now, I'm just gluing the board to the tiles. I'm going to flip this over and glue the LEDs to the tiles in a second step. All right, let's remove the tape here, flip this over, and glue the LEDs on. Okay, I've glued the circuit board to the back of the tile, added wires for the input, output, and programming lines, and I've also built this section of wall, which is just 2x4s and then a piece of drywall. When I thin set the tiles to this, it should represent a wall pretty well so that the taps are realistic. I'm going to add some thin set and get these tiles on there. I've got my mock-up of a wall here, complete with studs. The tiles have been mounted, and the first thing I did once the thin set dried was actually break it. Let me show you what happened. You might recall that the circuit boards that I'm using have these fingers where the LEDs mount as well as the microphone. These get bent at 90 degrees and then go into the space between the tiles. Now, the position of the circuit board is also important because both microphones need to be touching the glass tile. The problem is that when you bend these to 90 degrees and then you correctly locate the board, the fingers are way too long and they stick out past the top of the tile. That's what happened to the prototype here. The finger's sticking a little too high, and once everything dried, I ran my finger over it just to see how high it was. Now, the LED is glued to the tile, and the circuit board isn't, so what happened was I pulled the circuit board off of the LED. Now, if this board was totally out in the open, maybe I could fix this, but there's just no way here. I really can't even see what actually broke. There's nothing to do but make another prototype. This is a small frame that I've printed up, which I will glue the circuit board to before I put anything on the tiles. This will locate the LEDs correctly and provide the right spacing between tiles. You can see on this fixture just how far those things are sticking up. I'm going to have to change the design of this circuit board to make those the correct length. So I've mounted a circuit board to this frame, and then I mounted it all to these tiles and put them on the wall.
And this is really more of just a mounting test because this circuit board is the one that doesn't have properly functioning microphones. But I did learn something important. On these frames, I have this center spacer section where the LEDs get glued to. I made it just one piece before, and it turns out that if you glue the LEDs to this, and then you glue the LEDs to the tiles as well, and you flex the tiles at all, you still end up putting a lot of stress on those LEDs, and I'm worried that that could break them. I made a small design change, and I split the middle of that. That way both these sides can move a little bit independently, and should hopefully reduce the stress. You can see that this one does still work. It's better if I turn the lights off.
This attempt was so close. I had everything mounted and it all seemed to work fine, but after I installed the tile onto the wall, the touch feedback was no longer working. It turns out that the serial data line had shorted to ground. There was this teeny little solder bridge between two pads, almost invisible. I was able to pull the tile off the wall because the thinset hadn't fully cured, and I did attempt to fix this, but I'm afraid that as soon as the pin went high, it attempted to pull infinite current, and we all know what happens when you attempt to pull infinite current. I've taken a step back and looked closely at the code that handles the microphones. Both microphones seem to have very similar values, which could be a real effect, but it turned out to be how I was handling the analog to digital converters. The way I was running them was to sample one channel in interrupt mode, and then switch channels and repeat the process. This didn't seem to be working though, so I switched to a continuous conversion approach, and I implemented an end of sequence interrupt. This mostly fixed the issue, except now there was another strange thing that cropped up. It seemed like after a while, on the order of a few seconds, maybe 10 seconds, the two channels would flip. I thought this might have something to do with interrupts breaking a process at an inopportune time, so I tried pretty much every combination of ADC settings I could think of. From simply polling in the while loop to using DMA. I actually had to tell the chip it was a PY32F030 to use the DMA, as the 002 allegedly doesn't have it. But none of these ideas seemed to work. Eventually, I was watching the ADC values run by on the debug window, and I realized something. It wasn't actually the ADC that was flipping channels, but it was the communication between the main processor and the PY32. Here's what I think is happening. For some reason, one of the external interrupts is getting missed, probably still due to overlapping interrupts and timing. I could actually occasionally see this on the oscilloscope, where I would only get one UART message. The main processor, the Nucleo, is expecting 2 bytes of data though, so if it only gets 1 byte, it just waits until the next cycle and interprets the first byte of that cycle as the last byte of the previous cycle, effectively flipping the channels. I solved this in 2 ways. First, on the PY32 code, rather than doing 2 UART messages, each one 1 byte, and 2 separate external interrupts, I switched to a single transmit of 2 bytes on the first interrupt only. If that one gets missed though, for whatever reason, the second interrupt is still active and has the chance to send it again. Secondly, on the main controller code, I added a function to terminate the UART receive during the period between LED commands. That way, if it doesn't get the full amount of data it's expecting, it won't matter. The next cycle will just start over, filling up the first byte. After implementing these, knock on wood, it seems to be working perfectly. Whichever microphone I hit causes the correct LED to change every time.
Okay, I've got these 3 boards built. They're programmed and ready to go. I'm gonna get them installed on these 6 tiles. Man, I hope this works.
Okay, here it is. The tiles are on the front here. These 6 are the new ones, and these up here are non-working previous attempts. The back is an unkempt rat's nest of wire, which is a signature feature of my projects. I've tested out the boards individually, and they all looked good. So now I've soldered all the outputs to the inputs of the next tile, so that these 6 are all effectively in a chain. I'm going to hook this up to the Nucleo and see what happens. There are just 4 wires hooked up here. Power, ground, the LED command signal, and the microphone return line. I've already made my sacrifices to the gods of electronics, so here it goes. Alright, well, no smoke, the LEDs work. No touch feedback though. Let me get a scope on this data line and let's see if I can tell what's happening. Okay, it was immediately obvious what the issue was. The serial line is only swinging about a third of the way from VDD to ground. I've accidentally put the UART pins in push-pull mode rather than open drain, which I need since I have more than one device talking on the same wire. So two of the microcontrollers are pulling that line high, while the third is trying to push that signal to ground. I'm going to get that fixed in code, and hopefully I haven't damaged anything. Alright, that took literally a minute to change. I also enabled the internal pull-up resistors. Let's see what we've got. As I figured, the internal pull-ups are totally inadequate to return the signal from ground back to VDD fast enough to keep up with the data rate I'm using. These signal transitions should ideally be straight up and down, but you can see that they have a very obvious exponential shape to them. It's taking about the same amount of time to return to VDD as it takes to send a whole byte of data, so clearly I need a stronger resistor. Alright, I've got a 4.7K pull-up resistor in there now, which should pull less than a milliamp, and it seemed like a good place to start. On the scope, I'm seeing a dramatic improvement, but it's still occasionally missing a reading, so I'm going to go a little stronger. Now I've got a 2.2K resistor in there, and the data looks correct, and the transitions seem reasonably fast. This should only pull 1.5 milliamps, well within the pin's capability. I could go to a stronger one later if I need to. I'm going to plug the microphone back into the controller and give it a go. It actually works. I mean, I wouldn't have built it if I didn't think it was going to work, but still, it's always satisfying when a project comes together. I know it's kind of hard to see the LEDs here. They're only running at 3.3 volts, so they're quite a bit dimmer, and of course with all the lighting in here, they kind of get washed out. Okay, I've played around with this for a bit, including looking at all the microphone values in the debugger, and I've had a couple of observations. The touch doesn't seem to work on a couple of these, but the microphones actually do work. They're just quiet. The really simple code I have loaded for this at the moment just reads the microphones, it finds the largest value, and it lights that tile up if the value exceeds a certain threshold. So if you tap on these quiet tiles harder, you actually just make a bigger value at the adjacent tile, and you make it seem like this one doesn't work at all. There are two things I'm going to change to fix this. One, the microphones are barely on these lower tiles. The microphones are different distances from each other on the board, and one goes about 3/4 of an inch onto the tile, the other only about 1/4 of an inch. The one that's further in on the tile seems to be universally the louder one. So I plan to make the boards a little bigger and get the microphones equal distances onto each tile. The other thing I'm going to do is implement some kind of a calibration routine in the software. I haven't quite decided how this is going to work, but one idea is to go tile by tile and tap them in some consistent way. I'll then measure how loud that tap is, and I'll use that to set the threshold for each individual tile. That way, a more sensitive tile will take a larger tap to get it to trigger, and a less sensitive tile will still be usable. Another thing is that these two tiles are really dim. It's probably hard to tell on the camera. One of the reasons for this is that the reflector on the back is painted on, and some of it actually gets on the sides as well. I usually scrape it off before gluing the LEDs in, but I got ahead of myself when I installed these. I need to make some kind of checklist or something to ensure that I hit all the steps for actual production. It's also possible that these LEDs aren't in the exact right spot, but I've already addressed that by changing the shape of the circuit board. I've really learned a lot from this prototype, and I'm pleased with how well it's all working. I've worked through a lot of bugs while making this, not just in the software, but also with the hardware and the mechanical mounting. I've got a new round of circuit boards coming to do one last prototype, but I think that I'm nearly ready to start putting tiles on the actual wall. Next, I'm going to be making a device to automatically program and test the boards, and then I'll move into building the actual tiles. Be sure to subscribe to stay up to date. That's all I've got today, so thanks for watching.